I'm here. I'm here.
Okay, good.
Will be
Orik, I cannot hear you.
now.
No. Do you say something?
I'm
I
saying
cannot. Yep.
yes. I'm saying
Sorry, I cannot hear. Others than yes, I'm saying. So I cannot hear your question.
okay. Uh, I want to ask where will where will it be?
Where will it be?
Like I don't know. That he said like the last train multiple.
Sorry, Fong. Um, I cannot hear
The
clearly.
connection, right? Okay, I will type. I will type.
Okay, okay. Or maybe share share your um pad, iPad, if it is easier for you. Whatever, which one? Sorry, because I don't know if uh, Jack can hear, can you hear you, but I think and anybody else can hear you, but I cannot hear you. Sorry. Okay, okay. So nobody here. Sorry.
Okay, can
Okay. Yes.
yes. Wait. Okay. Question is because yesterday he said like there's you value only. So hear me?
Hmm? I cannot see. I cannot hear. I
Weird. Uh,
Yes, Wong? No, I cannot hear. Sorry. I maybe you unmute yourself. Oh, okay. It's that. How can Okay, good question. So so basically, yes, Lagrange multiplier is only to find minimum or maximum, or if it is not convex or if it is not concave, maybe only extreme point. But when when the equation has the constraint, so if there is no constraint, we don't need to use Lagrange multiplier. Only when there is constraint. Um, when there is no constraint, we just derive using partial derivative for multivariable function and make sure that the partial derivative equal to 0, and we will find the extreme point. But if there is a constraint, maybe the extreme point of the function is outside the constraint. So uh, it is not what we need. So how to say? Uh, for example, we search for the cheapest food, okay, and we in the internet. So we find that the cheapest food maybe there is a rice with a duck with a vegetable only for 50 NTD, very cheap, right? But when we find the location, the the location is in Sinzu, for example. So uh, it's become not cheap anymore for us because the transportation from here to Sinchu is much more expensive than the price of the food. So we need to find a cheapest food, like not only in Taipei, because if it is in, let's say, in Shilin, it's still far away, and it's so maybe the cheapest food around maybe less than 100 meters from NTST. That's example of the optimization with constraint value, and it is, well, it's look quite limited, but as engineer, we use it a lot, like lot. So for for example, for myself, because I have graduated from master degree some years ago, and my thesis for master degree is related to Lagrange multiplier, basically. So yeah, Lagrange multiplier only find extreme value, but basically we as engineer most of the time try to find the extreme value. What is the cheapest? What is the, if we want to sell product, what is the highest? What is the price so we can get the most money? Because if we sell too cheap, then we we don't have we don't get uh, the most money. But if we sell too expensive, we also don't get the most money because nobody buy. So we need to find some kind of optimum value. And I think most of the time, it is what we are doing is in engineering is just to find extreme value. So yes, Lagrange multiplier only works to find the extreme value, but well, it is more advanced level. So if right now you learn about physics is Newtonian physics, but actually for there are more advanced physics that's call it Lagrangian physics. Let me type. If you interested, maybe Lagrangian mechanic. It is more actually it's quite useful, especially for some field like chemical engineering, etc. And basically, it is apply Lagrange multiplier on physics because how to say uh, I think it's not relevant for us for now, but yes, it is only to find extreme value. But in life, most of the time, what we need is just to find extreme value. Is it clear so far? Or can you hear me? Okay, good. So, I okay. If I might, I want to explain a little bit about uh, like Lagrangian multiplier. So what it so what it is. So okay, good. Wait, I want to find the pen, 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 pen. Ah, sorry. Ha. Okay. So suppose this is a function, okay? This is function f. So we know that the gradient is basically the elevation of this function. So for example, this one is positive. The gradient is positive because this is x, right? So if we increase the x, we increase the value of function. And here maybe here maybe the gradient is negative because if we increase the x, we decrease the function or something like that. It is not only x but also x on on all variable x, y, z because we know. Sorry, this is only x, y to z. So because function is function x, y to the z. Okay. So if we have the gradient that is df dx comma df dy equals to 0, but remember that 0 is a factor here. So 0 to the x and 0 to the y is basically here. Here, which means that there is no elevation there. So it is either the minimum or the maximum. And as you can see in the book or in the class, uh, you can check whether it is minimum or maximum with the extreme value and the area in the boundary. In the boundary. Actually, there is just like, do you remember, right? In the first variable you have a second derivative. Actually, here we can also have a second derivative. So if second derivative of fx, so second derivative is something like this. If fx y is, it's not positive here because it's basically a matrix, is, we call it positive semi-definite. So the function is convex. This is convex. If it is negative, it's become, if it is negative semi-definite, it's become concave. But this material, positive semi-definite, and is outside calculus, our calculus, so we don't need to care about this. What we need to see is uh, the extreme value and the border. Now, let, let me talk about now. Let me talk about what 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 we mean by a constraint. So suppose, hopefully my drawing is not that bad, but I'm sorry if it is bad. It's kind of not good, but okay. So suppose we have the donut gx y z. Okay, this is on the, it is on the 3 dimensions. So x, y, z. Oh, sorry. Before I get it wrong, it should be x, y, z because of the right hand rule. Sorry, I make mistake. So it is true now, x, y, z, and we have the donut g. Now we want to minimize a function f. Function f. So I want to make it clear. Okay, f x y z. The f in the donut to the constraint. This is the function, and the donut is the constraint. The, the constraint is g, and this is the donut. So what does it mean? So suppose we have, this is the dot. This is a point in G, right? We have a value of, this is x0, y0, c0. It doesn't mean anything. It's just first point. So we have f in the, a value of f in the x0, y0, z0. So now what is the gradient of f? So the gradient of f is somewhere something like this. Yes, this is the gradient of f in x0, y0, z0. what why this is the gradient. Now, before in the previous one, for in the two in this example, if I have, for example, I begin in this point, how to decrease, how to de- how to get a lower value of x of f. No, well, we know that gradient is elevation, so what we take is just for minus gradient. We will guarantee that the value will go down. So for example, this is the gradient is negative there. So we took the minus one, we go to the right. So we will decrease the value. While here the gradient is positive, so we took the negative, it's mean to the left. So when we go to the left, it's go down. Okay, this one is in the non non constraint one, but now we have the constraint of the donut, and as we can see now, the gradient is not stay in the donut. The gradient is somewhere living out of the donut. So what we do here now, where we go in the donut is we took the projection of this gradient to the donut. This is the projection. The projection. Okay, I will stop here for a moment and I will see you guys. Do you understand so far? Do you understand so far? Can you reply to me, type or whatever? Do you understand so far? So uh, basically what I do here is I want to get a low, let's say I want to get a minimum value. So before I took gradient and took the negative. If I want to get the maximum value, I took the gradient and follow the gradient. But now, because the gradient doesn't stay in the donut, what I do is I took the gradient and the project to the donut. So, and follow the projection. So far, so good. Okay, understand. It's okay if you're confused, but it's not easy. Let me make it a little bit clearer. Okay. So what I want to say is, instead of the gradient of f, what we need is the gradient of f projected to g, or in the simple way is df. It is like this is cos, right? Cos theta. So basically it is the cross product, the cross product, because it is cos is dot product of gradient f with the donut, with this vector. So the donut, and we get a projection of f. Okay, doesn't you doesn't need to think about mathematics so much, but do you guys can imagine these donut things in your head? Yes, okay, good. That is, we talk about gradient of f. Now, what is before we know that the gradient f we want to be equal to 0. Here in this interpretation, what does it mean to be the gradient of f is 0? It will be minimal. What does it mean? Uh, it is it is hard to imagine, but what it means is the gradient is normal to the g. So the gradient f here is normal or perpendicular to the g. So if it is normal, we cannot project. The projection to the g is 0. Understand? Do you guys understand? So if we want to be to in the so before we want the gradient 0 is basically it stay flat. Now what does it mean? It's mean that so it is gradient equals 0. Now because the gradient doesn't stay on the plane, it's maybe something like this. So if it is 0, it's mean that the gradient of f is perpendicular, normal. It is normal to the to the to the to the constraint, to the donut. Okay. Now my my question is, what is the gradient of g in g? So basically gradient of g in g is always 0 because, well, g in g is constant, right? It doesn't change. You move from here to here to here to here, it's still on, always on g. So the gradient of g always constant. Always, so g always constant. It means the gradient of g kind of 0. But it is not gradient of f equals 0 or gradient g equals 0. It's not that. What does it mean? That doesn't matter where, in as long as in g the gradient of g is always normal to the g. Makes sense, right? So remember that gradient of g is always normal to the g. So what is the extreme value here is in a point here when both gradient of f and the gradient of g and the gradient of g equal normal to the g, perpendicular to the g. So it's mean that the gradient of f and the gradient of g is perpendicular to the g. It's mean that it is on the same direction. So the gradient of g and gradient of f should be in the same direction. But we know that gradient g is always normal to the g in g. So what does it mean? But in the same direction is basically it is the same. It is the same value, or well, because both gradient both these things are vector, right? So when we say that it is in the same direction, it means that one is the multiplication of the other. That's basically how Lagrange multiplier comes from. So the gradient of function and the gradient of the constraint must follow the same direction when what? When the gradient of the function is normal, when it is normal to the constraint. So far so good, or do you guys more confused than before? How? Can you hear me? How? Any comment? More confused? More clear? Okay, got it. Yeah. How about the other? So the story is about how to find the grad when the gradient f is also normal to the constraint. When it when the gradient f the same as the gradient g. So yes, that's why it is an extreme value. Exactly. Wrong. Exactly. So it's the gradient is not zero. It is normal to the constraint. So it is not zero. That's but that I mean that's okay. But I mean, well, I as information yeah, last semester I took a class. We jokingly say it is the calculus uh, for master and PhD student, and yeah, so the class is only learn about Lagrange multiplier, and it is so Lagrange multiplier can be, well, if you want to really understand Lagrange multiplier, it's need a class, uh, a course, a thought of one semester, and even that, if I'm not mistaken, half of the student fail, and all the students are not undergraduate. All of the students are master and PhD, and I think like half or quarter of the student fail. So if it's okay if you don't understand, but I hope you guys can have some uh, mental image, but yeah, why it's extreme value. Okay, I think it's clear enough for the Lagrange multiplier. I think it's the best thing I can explain to you guys with all you already know so far. Is there any question about this or about other things? No? Okay. Okay, fine. Like time. Good. Can I think about Lagrange multiplier as a point? No. Lagrange multiplier is this is this is lambda, and it is remember that Lagrange multiplier is scalar, not a vector. It's multiply a vector of the constraint gradient, or you can put here, doesn't matter, because for example if it is 2, if you want to put here it's become half or something like that. So no, Lagrange multiplier is not a point, it is a scalar that only show that yes, but at that point both the gradient of the function and gradient of the constraint has the same direction. So the point, we call the point extreme point, but the the multiplic the yeah, so got it. So the comparison between the constraint gradient and the function gradient, we call it Lagrange multiplier. Because why? Because the inventor is Joseph Lagrange. I I forget how to spell his name. Is French, but maybe you in Vietnam has better French pronunciation than me. But it is a French, and so basically, it's not a point, but comparison of vector. Okay, okay. Thank you. You got it. Uh, any other question? Okay. If there is no question, can you try to do some exercise? Here the exercise. So basically the question is find the partial derivative in this point in this point to this direction. Okay? Is it okay for you to do this exercise? Wait. What form? What you done? Can you open your mic or can you type explain something? Wong? So yeah, please do exercise. Just do this first one, and please tell me when you finish doing it because I think um it's easy, but if you never do it, you will be like, huh? How to do this exercise? So I think it's quite interesting to do. So just doing this first one, square root of 2x plus 3y in this point in this direction. So here I we have minus, this is u, and u is minus phi over 6. Why this disappear? Minus, so basically 30 degree. 60 degree. So this is 1, 2, square root of 3. So u is equal what? 1 comma square root of 3. df is here equals to 2 over 2 square root of 2x plus 3y, comma 3 over 2 square root of 2x plus 3y. So at the point 3.1, it's become 2 over 2 9, 3 over 2 square root of 9. 1 over 3, comma half. This one times this one, so du is 1 over 3 plus square root of 3 over 2. Is it the same to you guys, or I make mistake, or what? Oh, okay. Yeah, I forget, sorry. So yes, u is should be unit vector. You're right. So it is should be what? Over 2, right? So this one and 1 over 6 square root of 3 over 4. Am I make a mistake again? Okay, so it's right. Okay, good. Clear, right? Everybody understand? Please reply. So otherwise, how did we get the u? Good. That's 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 the reason I put this exercise. So look at the angle is minus phi over 6. So basically minus 30 degree. So this one, how we get the u is, this is 30 degree minus. So it is in the quadrant 4. So this is, the x is 1 and the y is square root of 3. Sorry, I should write this. this is x, this is y. So we got this, and as Jekai said, that it should be normalized. So square root of, so 3 plus 1, 4, square root of 4 is 2. So yeah, it's normalized to this. Is it okay? How is it? Do you understand how to get the u? Mm, okay. So that's why I put that. Check if there is interesting question about because, well, partial derivative is pretty easy. Because you just derive function to the x, and you consider y and z as constant, and after that you derive function to the y and put and assume x and z as constant. That's why we call it partial derivative. That's that's I think pretty, the partial derivative itself is easy. To find minimum value is also easy. Just partial derivative when equals 0, all equals 0 if it is not constrained. If it is constrained, just use the Lagrange multiplier. And oh, do you guys know how to find the value of Lagrange multiplier? Do you guys know how to get the the how to get the value of Lagrange multiplier? Okay. Uh, Sorry, let me think about it. The problem is it's not hard, but you need kind of linear algebra to solve the functions. So ho, 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 ho. Let me check if there is example that you you don't need. Okay, it is from the book. Okay, well, of course you can read by yourself, but let me give some kind of guidance. So here we have the function is f v, and the constraint is g, and then basically what we want to do is find when oh, sorry. Okay, so find when the gradient of f of v and of g is in the same direction. So basically this one. So v to the x, uh, so partial derivative of v to the x is the same direction of partial derivative of g to the x, to the y, and to the z. And don't forget that it must fulfill this constraint, the g itself. So from this to this is it's easy because this one is because v is xyz, right? So the derivative to the x is yz, to the y is xz, to the z is xy, and the right is also with derivative of this part is of this guy is also, well, you know how to do it. Now from this to this, it's not hard basically, but well, no, sorry. So how what they do is to make sure that the left all these three left side is the same. So this one is yz, so I multiply with x, xyz, the right also x, multiply with x, so become this. So left become the left part all become xyz, and the right part become this. And now it's just you you solve the things using linear algebra basically. But it's just like if you remember the price of two apples plus three orange plus four guava is like 100, and yes, it's you know that's linear variable algebra. It's just um, it's you have learned that on the high school, right? It's kind of solving three variable equation. Can you reply to me? Have you learned that's three variables? Can you solve? Can you guys solve three equation system to find three variables? Okay. Okay. Yes. Basically, solve that, and you get the minimum, the extreme value. Uh, Most of the time, we don't care about the value of Lagrange multiplier itself. But I give you some intuition. What does it mean if the Lagrange multiplier is 0? What does it mean if the Lagrange multiplier is infinite. So what does it mean is if the Lagrange multiplier is 0, it means that the function doesn't have constraint. That's all. If the Lagrange multiplier is infinite, it means that we don't care about the function, we just care about the constraint. So in the example of the food, for example, I want to find a food in Taipei. So the constraint is the Taipei and the price is the function. If the Lagrange multiplier is 0, it means that there is no constraint. I don't care if the food is in Taipei, or in Tainan, or even in maybe in Chinmen or whatever. I don't care. As long as it's cheap, that's what I want. If the food is if the Lagrange multiplier is infinite, it means that I want I'm lazy. I mean, not lazy in the bad way, but it is now kind of a lockdown, right? So it's okay if I pay a more expensive as long as I don't move from my house. So as long as the constraint is I don't want to move to leave my dorm or my house. That's the constraint. It's okay if I pay more expensive because I ordered from Food Panda, for example. That's the constraint. So what is in real life? How we define, how we choose? Well, basically it depends on the situation. If it is only food, I think it's okay if we order from Food Panda. So it just like I don't care about the function. I just need what I want to do is just follow the constraint. The constraint is kind of locked down. But on the other hand, if I want to I have a factory, I want to buy iron ore, for example. It's okay if I even buy it from South America or even from Australia, if far away, because I need a lot as long as it is cheap compared to if I buy in Taiwan but it's expensive. So in this case, the Lagrange multiplier becomes 0 because there is no constraint of location. The constraint is 0, but I need the function to be minimized. I want to get the cheapest iron for my factory. So when I program optimization, usually there is no there is no formula to find Lagrange multiplier. We just try to to get to solve ours, to get the best Lagrange multiplier in order to solve our problem. That's it. So as long as I know there is no real formula to solve, maybe for some problem there is some very small problem there is a way to solve Lagrange multiplier, but most of the time there is no way to solve the Lagrange multiplier. But yes, there is a way to solve the minimum, the extreme point. I think that's the point. Is it clear to you? Clear? Okay. Is there any more question? Nope. Okay. If it's clear, um if you need something, if you want to ask something after this, you can send in the Moodle. Usually I will answer it in the 24 hours. And I think that's it for today. Thank you for coming to the session and see you next week. Bye bye.